All right, Dean. Well, thank you, and thank everyone for joining here this afternoon. You should be seeing my screen here. So Dean kind of teed this up very well with kind of the relevance of looking at fan energy regulations today, and how they're playing into codes and DOE regulations and California Energy Commission and just a whole bunch of different regulatory elements. We're going to touch on those, but the other thing I really want to focus on is kind of the title of the slide is Beyond Compliance. FEI is really a pretty neat tool in that it not only is working as a compliance tool, but it's really a selection tool that helps all of you select better fans for your applications. So that's what we're going to share with you today, and hopefully by the time you get done here, you'll see the value in it and understand how to specify and include FEI in your fan schedules. All right, so basically we've got 4 different areas of the presentation. First, we're going to start just talking about exactly what is FEI. We're going to talk about how it how it ties to fan system selection. When we say fan system selection here, the term system can be a bit confusing. But when we get into it, we're talking about the fan that encompasses everything from where the electrical power comes out of the wall, into the motor, into the drive, belts, pulleys, including the aerodynamic performance of the fan. Not necessarily the fan distribution system, but the overall, just the fan, entire fan itself, which is different than what the way fan power was measured and published in the past. Then we'll get into the code adoption and compliance issues, and finally, wrap up with some recommendations at the end. Okay. So, what is FEI, Fan Energy Index? Dean referred to it as Fan Efficiency Index, but really, we want the emphasis is on energy. FEI is a tool that, first of all, can be used to accurately compare energy consumption of one fan to another. And you're going to hear this multiple times, but in the case of FEI, bigger is better. So an FEI of 2 compared to an FEI of 1, that fan with an FEI of 2 will use about half the power of the fan with an FEI of 1. So again, just a simple ratio that allows you to easily compare the power consumption of 2 different fans. Secondly, as I kind of alluded to already, it's a tool to help you select the best fan for your application. We'll get into showing you how it fits into a fan curve and defines really a compliance or an ideal selection range within the fan curve. Okay, to help drive better fan selections. And then third, it is a mandate right now. It's in ASHRAE 90.1. It's in the latest edition of IECC. It's in the IGCC, which I believe Massachusetts may be using now, the stretch energy code from 90.1 or IECC. So we'll talk about the mandates as well. All right. So that's what a fan energy index kind of is in a broad sense. More specifically, though, in terms of how it's calculated and what this ratio means, if we start looking at the right side of the screen here, like I said, it's a ratio of the baseline electrical input power to the actual electrical input power of the fan. So therefore, as your actual power for your duty point goes down, the FEI will go up. And if we look at the curve on the right side or on the left side of your screen, you can kind of see where these FEI bubbles, as we call them. We've got an FEI of 1.0 there along the kind of the right side of that fan curve. In ASHRAE 90.1 and IECC right now have established a minimum FEI of 1.0. So what that's basically doing is it's forcing all fan selections to be up in this blue shaded area of the fan curve. All right. So thinking about it another way, everybody knows, hey, we don't want to operate over here on the left side of this curve where we're in the stall region. But a lot of people didn't realize or understand that, when you're down in this lower right part of the fan curve, that's probably where the fan, well, not probably, that is where the fan runs most inefficiently, and it's going to be louder and use more energy. So FEI is just kind of bracketing the fan curve to drive selections to what I'll call the sweet spot of that fan's performance capabilities. Okay, so as far as the electrical input power, where did that come from? Well, first of all, it stemmed from a ton of research that AMCA did many years ago, where they looked at a scatter diagram of fan selections over the entire flow and pressure range that a fan could work in. So basically, you've got infinite selections, okay? And they graphed that and they said, okay, for any given duty point, what's a reasonable power consumption for that duty point? And based on some statistical analysis, they came up with a baseline power for for the entire spectrum of flow and pressure. All right. But when they did that, because FEI is a wire to air metric, they had to take into account what are going to be the drive losses for the motor and the V-belt drives, because back prior to FEI, fan power was based, and manufacturers just published brake horsepower. And brake horsepower does not include drive losses of the belts and pulleys. It does not include losses of the motor. So in developing that baseline power, AMCA engineers also made some assumptions relative to what the motor and drive were going to be. And then they said, all right, we're going to establish an FEI or a baseline power for each duty point. And that's going to be what we use, going forward into however far we use FEI into the future. All right. So FEI, based on a lot of historical references, we made some assumptions relative to the motors and drives, and we established a specific, one specific baseline power for each point on a fan curve. So if we look at it from a fan perspective, what is the actual electrical input power? Well, as I said, it accounts for all power from the electrical power into the motor, which you can see here on this graphic. It accounts for drive losses, it accounts for VFD losses, accounts for bearing losses, and accounts for aerodynamic losses. You say, well, okay, that seems to make sense, but that was not happening up until manufacturers have started using FEI in their fan performance publications, or in their fan performance ratings. Brake horsepower does not equal actual electric input power. All the brake horsepower accounts for are bearing losses and aerodynamic losses. So what that means is all these other losses that we have between the power into the fan and the air power out of the fan were not being accounted for. So things like VFD loss, which can be somewhere in the neighborhood of 3% loss, motor loss can be up to 10%. Drive losses for belts and pulleys can be another 3 to 10%. Those were not being accounted for when we were just publishing brake horsepower. All right. So again, from that standpoint alone, FEI is a much more robust and better way to make your fan selections. So as I kind of said, FEI, it's truly a wire-to-air metric that rates the overall energy consumption of the complete fan system, not just the fan and bearings. All right, any questions so far, Dean? We're all good?
Not yet.
Okay, I'll keep trucking then. So how do we use FEI in making fan selections? And how does it work? So advantage of FEI is that, higher FEI, as I've already kind of alluded to, equates to lower energy consumption. Lower energy consumption ties to lower operating costs, and lower energy consumption is going to tie to lower carbon emissions as well. All good things for, you as the engineer. It's good for the owner, and it's good for the environment. The other thing from a, kind of from your perspective, assuming we have engineers on the line, but even contractors for that matter, FEI is typically going to drive you to a more forgiving fan selection. So if you do not have your static pressure calculated perfectly, or if you need to speed that fan up or slow that fan down, it's going to get you, again, as I said, into that sweet spot of the fan curve that's going to allow for a more forgiving point of operation on the fan curve. And then, also when you have a higher FEI, generally the fan's going to operate a little quieter. And then the other cool thing is when you're doing your submittal reviews, and we'll talk about adding FEI to your submittal, your fan schedule on your submittals, it's going to allow you to quickly highlight potentially inferior fans or fans that are being, bid or supplied that are not necessarily apples to apples comparisons. So we'll give you some guidance on that as well. So first of all, let's look at three different fan systems here. Okay, three identical. They're not identical fans, but they've got an identical duty point. We selected these fans at what did we pick here? 3,500 CFM and 1.5 inches of static. All right, and they're all three square inline fans. And so when you look at, if you're using a software selection program that shows, the basic fan performance, sound, motor horsepower, and brake horsepower, you say, well, which one uses the least amount of energy? Well, if we're just basing it on brake horsepower, they all have identical brake horsepower. All right. So you really don't know for sure which one uses the least amount of energy. Now, if you know anything about the Greenhack model designations, you know that VG in the model designation means that fan is equipped with an EC motor. Well, an EC motor is probably the most efficient motor technology on the market. So if we take that into account, which we do with a wire-to-air metric like FEI, you'll see when we add the FEI column in here, EF2 is the one with the largest FEI, and EF2 is going to be the one that consumes the least amount of energy. All right. So again, FEI is a very good tool, a much better tool than what we had in the past to actually base to give you the true indication of what that fan power is going to be for the electrical output or electrical input power to that fan from the wall. All right. So you say, well, why, what's driving the difference here? Again, remember, brake horsepower only accounts for aerodynamic losses and bearing losses. FEI is accounting for motor losses. So in this particular case, each fan has a different motor. So EF1 has a 6-pole motor with a VFD. Because that's a direct drive fan, we had to hit it with have a VFD on it to get it to the operating point. EF3 is a 4-pole motor with a VFD, where EF2 is an EC motor with a built-in drive, so that again, as I said, it's going to be the most efficient motor drive combination of the 3 motor drive selections in this grid. All right, so what does that mean? A 1.4 versus 1.28, that's, what is that, 0.12 difference in FEI, about a 9% difference in power consumption is what it amounts to. So if we put some numbers to this and we say, all right, if we have this fan, say the most efficient fan with the least energy consumption compared to the fan with the highest energy consumption, what does that mean over the course of a year? Well, so for 1 year, that's about 534, just roughly over 500 kilowatts of energy savings. Based on average U.S. energy cost for electricity, it amounts to about a $64 energy savings. And if we look at the typical CO2 output for a kilowatt of energy, it equates to about 450 pounds of CO2. So you're looking at that, probably saying, well, yeah, that's nice, but it's not moving the needle a whole lot. So you say, well, you're not going to have that fan operate for just 1 year. You're probably going to have it operating for multiple years. So, what happens over the course of 10 years? And, real easy, we just add a 0 to everything, right? Well, now the numbers start to get a little more interesting. And then if we take it to the next level and say, well, how many times do we have just a single fan on a job? Probably not often. So what if we've got 10 fans on that job operating over 10 years? Now the numbers start to really add up. 53,000 kilowatt hours of energy savings, roughly $6,500 of cost savings to the owner. And from a sustainability environmental standpoint, which is actually starting to take more of a having more influence on some of our fan selections than even power and cost at this point, you're going to reduce your CO2 output on that fan by, what is that, a little over 20 ton of CO2 emissions. So small difference in FEI can make a big difference in the overall energy cost and carbon footprint reduction of a fan. Second thing we said, well, it's a more forgiving, drives a more forgiving selection point. So if we look at the fan on the left, it's a belt drive fan. The fan on the right is a direct drive fan. And you can see, because we're taking into account the belt and pulley losses now on the fan on the left, the FEI compliance bubble is going to be much smaller than the FEI compliance bubble, or selection bubble on the direct drive fan. So, I think it goes without saying, if we have a selection point in the, somewhere in that blue range, the fan on the right just has a much more forgiving, it has much more flexibility in terms of where that, if the duty point is not exactly where you calculated it, or if you need to speed this fan up for some reason, the fan on the right is going to give you much more flexibility than the fan on the left is going to give you in terms of staying within that FEI 1.0 compliance bubble. All right. And then as far as a sound and size relationship, it's fairly, I think, for those of you who've been doing fan selections for a while, when you have a larger fan's going to run slower. When the fan runs slower, it's going to be quieter. Well, the same thing applies here with FEI. If we look at these two fans, again, the fan on the left is going to be a smaller 24-inch fan. The fan on the right is slightly larger, even though you can't see it here. But I guess if you go down and you look at the graphic on the bottom, we've got a 24 versus a 36-inch fan. Again, both operating at the exact same duty point, but you can see the larger fan is going to be significantly quieter than the smaller fan, and consequently the FEI is going to be quite a bit larger as well. So again, larger FEI typically equates to lower sound levels as well for the same fan type. Should qualify, you need to be looking at the same fan type. You can't mix an axial fan and a centrifugal fan. That won't necessarily hold up. But if you're comparing two axial fans or two centrifugal fans or two inline fans, this is a pretty sound rule of thumb. All right, so then let's talk about how using FEI in your fan schedule and in your specs can help you kind of uncover maybe some red flags when it comes to reviewing manufacturer submittals. Okay, again, a small difference in FEI can kind of relate to some pretty significant changes in the fans. So one is, we kind of touched on it already. If we kind of go down the checkbox here, are both fans using the same type of motor? Chances are that a difference in FEI is because one fan has a more efficient motor than the other. For example, it's have an EC motor or an induction motor. The next one, pretty obvious as well, but is one fan a belt drive? Is one a direct drive? Are the differences in motor voltages or phase that might be causing a difference in the FEI? Does one fan maybe includes a VFD, one does not include a VFD? That can make a difference in the FEI in it. And then finally, the impeller might be a different style of fan altogether. Mixed flow versus a centrifugal wheel, or an axial versus maybe a vane axial versus a centrifugal inline blower. So there can be a number of things that are not per your specification or not as you had desired the fan to be, and FEI is a good indicator of the need to run up some red flags and ask some more questions if the FEI is not being met. Okay, so again, in general, higher FEI indicates a better overall fan selection. All right, Dean, again, pause. Any questions? I'm never sure if that means I'm just
Yeah, so there is
Okay.
one question here. In a replacement fan project, is there a way to determine FEI of the existing fan for a better projection of energy use?
Boy, that's a great question. Well, say that again. For a replacement.
for replacement fan projects. So I think what they're trying to look at is the FEI of the existing fan
Existing.
versus the new fan that they're putting in,
Um,
and the the efficiency and energy reduction in energy
yeah.
usage.
Yeah, that could be done. You'd have to run an estimate on your drive and motor losses. I believe AMCA has an FEI calculator on their website. So I guess I'm trying to think of how to do this. You'd almost have to go in. You'd have to find the original performance data. So you've got brake horsepower off the original performance data. Oh, actually, an easier way. If you know your electrical uh, input current to that fan, you could calculate your electrical input power by knowing the amperage into that fan, the amp draw of that fan, and you could back into an FEI that way, knowing your flow and pressure. Yeah, you'd have to you'd have to do some field measurements on your flow, pressure, and electrical amp draw of that fan, but you could back into an FEI for your fan in the field. It'd take a little work, and then do a comparison to whatever replacement fan you're looking at swapping out. So yeah, it could be done. It would require a little work. It's not something that's readily available, but I'm sure whoever the manufacturer of the fan is could help you with that. Or Dean, regardless of whether it's a Green Hacker or somebody else's fan, you guys could help with that, or we could go to AMCA, get some help with it as well. But yeah, you could do that.
Okay,
All right. Okay, I'll keep going here. So now we're getting into, we kind of talked about the beyond compliance. Now we're going to talk about the compliance piece of it. All right. So FEI and code. So this has been somewhat of a journey in terms of how we've gotten to where we are. It actually started back in 2011, but as far as the fan energy index, FEI goes, that really became real in 2017. AMCA developed this metric. Dean kind of made reference to a prior metric called FEG, which AMCA scrapped and said, hey, that there's some flaws with that. So here's this FEI, Fan Energy Index, is a better metric, and here's a standard for it. So that was published in 2017. That was picked up very quickly by ASHRAE, and ASHRAE adopted FEI into 90.1 in its 2019 version. All right. And basically it said, any fans in, any projects that are being built in accordance to the 2019 version have to have an FEI of 1.0 or greater. And then we flash forward to today. There's actually mandates in place in the state of California right now called California Title 20 that no manufacturer is allowed to ship a fan into California that has an FEI of less than 1.0. So California has taken it one step beyond the codes, and they've actually put a regulation in place that kind of passes the burden onto the manufacturer. Okay, and that became effective basically the 1st of May this year. And then the DOE is also remains very active. They've published a proposed rule on fan energy requirements based on FEI as well. The requirements are based on equipment class, though. It's not just looking at fans as an overall equipment type. It's actually going into the different types of fans, which we'll talk about in a minute. Now, once the DOE rule would go into effect, that would preempt these individual state regulations like California Title 20. But the way DOE works, that at the earliest, that's going to be 2029 before we have a national minimum FEI standard in place for the entire country. So between now and 2029, we're going to be dealing with codes. We're going to be dealing with individual state requirements, and we'll be moving towards the mandatory requirements of DOE at the earliest 2029. All right, so let's look at the kind of a state-by-state adoption level of ASHRAE 2019. You can see the states in dark green there are states that do have an energy code that are as compliant or as energy efficient as the 2019 version of 90.1 would be. So generally, I guess we'll just focus on Massachusetts. You guys can see your dark green. In fact, I'm trying to, Dean and I were talking before the call. I think I was out in, well, I know I was out in Boston back in April sometime. And if I recall correctly, you guys, the state was in the process of adopting 2019. So I'm assuming the 2019 adoption is relatively new for Massachusetts. The other thing that we should probably be aware of is I believe Massachusetts does not use 2019 or 90.1. They use 189.1 in IGCC, the stretch code. So basically, it's going to be, everything in 189.1 is 10% more energy efficient than what's in 90.1. So that's something else we should be aware of for Massachusetts. Okay, but we'll come back. We'll talk about that a little bit more going forward. Here's these different equipment classes that the DOE is proposing. Again, you can see, it's proposing minimum FEI levels based on the type of fan. This is still just in the proposal state. FEI or DOE has not published a final rule on this yet. We've been expecting it all summer. Hasn't happened. Now with the presidential race heating up, I'm starting to lose hope that the Biden administration is going to get this done either. But we'll see. Time will tell. So, FEI is in codes, it's in regulations, but there are some exceptions, okay? The exceptions fall to basically any fan that's in another piece of equipment that's already regulated. So the way I would think of this, instead of trying to think about fans that are, in equipment, if you've got a fan that's a standalone fan that's not part of another piece of equipment, you probably need to be you probably will need to be meeting the FEI requirement of the code or the regulation. Okay, ceiling fans are exempt as well because DOE already has a separate regulation on ceiling fans. Fans used in critical applications such as explosive environments, maybe some life safety applications, are also exempt from the regulation. Thought being that they don't run all the time, so energy efficiency isn't that critical. It's more about the function of that fan. High temper applications might be another one where you get some exemption on it. And then lastly, fans that are under 1 horsepower are also exempt. So small fractional horsepower fans are still exempt from this regulation as well. Okay, now let's talk about third-party performance ratings. I'm guessing most of you, probably everyone on the call, has in their specification that the fan shall meet or comply with AMCA certified performance ratings for air performance. Okay, there is another new certification that AMCA has come out with. It's called FEI. AMCA has a standalone certification for FEI. So first of all, I'd encourage, and we'll talk about it, getting this into your specification. The thing that FEI does, or the thing that AMCA does, the way the AMCA program works is manufacturers will test a family of fans, say from, a typical family of fans might run from 24 inches in diameter up to 72 inches diameter with several sizes in between. We'll do that testing. We'll come up with our performance data for each one of those fans. We'll submit that to AMCA. AMCA will take a look at our data and they'll say, all right, we want to, they'll just randomly pick a size to be tested. We'll send that fan down to the AMCA labs. They will throw it on their chamber and they'll verify that the fan performs, to the performance levels that we're planning to publish to the marketplace. So again, there's an independent third-party process involved with verifying the manufacturer's data. Then once we've done that, AMCA has a follow-up program where every 3 years for family fans that are in the program, every 3 years they will randomly select another fan for us to build and send to AMCA, and it has to continue to comply. So, let's say for example, the first go around they tested a 36-inch fan. 3 years go by, next time they might call for a 24-inch fan or a 42-inch fan or a 72-inch fan. So it really is a quality compliance verification on the fan performance for the fan manufacturers, and it's a good thing and something that that from a specifier's perspective and owner's perspective, you want to have on your fans. So there's three labels here shown. One is FEI, there's an air performance in FEI, and there's sound and air performance. Basically, AMCA's probably, I'm anticipating we're going to do away with this air performance one because FEI basically encompasses air performance. So at the end of the day, you really want to make sure you're specifying, FEI, AMCA certified FEI, and AMCA certified sound performance on your fans. So again, nationwide adoption of FEI it's in progress, but it's probably a ways away before it becomes mandated nationally. But the journey has begun, the journey continues, and it's not going to end. All right, so I guess again, Dean, I'll take a pause there on that section if anybody's got any questions on codes and regulations.
None currently.
Okay, so kind of coming down the home stretch here then with compliance and recommendations. Recommendations is that even if your state is not adopted the most current code, we'd recommend updating your specs and schedules to include FEI as required by the latest edition of the code. All right, so even if you're not doing projects in Massachusetts where the code is up to date, I'd strongly encourage you to add this to your spec anyway. It's just going to get you a better overall system. Like we said, the FEI goes beyond compliance. It's just going to get you a better fan selection. Make sure you're using up-to-date fan selection tools like ECAPs. Most manufacturers now have already updated their literature and their software to include FEI. Again, that was largely driven by, anybody that wants to do business in California had to have their FEI stuff in place by the 1st of May. So that's probably done for most manufacturers now. Again, use caution if you're presented with an FEI that's less than what you've selected. Lower FEI typically indicates there's some sort of a either a difference in the motor, difference in impeller, difference in whether it's a belt drive or direct drive, something you ask a few questions on and drill into why there's a difference. So that brings us down to, basically schedule and hold the duty point for the FEI values for all the reasons I've just mentioned. Okay, now having said that, I wouldn't recommend starting your fan selection based on, maximizing your FEI or getting the highest FEI level. Start out with, selecting your fan based on the application, okay, and duty point and space constraints and all the other things that come into play when making a fan selection. Once you've narrowed that down, then I'd hone in on, okay, let's hone in on the FEI and, find an FEI that's going to maximize the performance of that fan and optimize energy consumption for that fan. So how does this look on a fan schedule? Pretty generic fan schedule here, but you can see we've added a column here over here, the third one from the right, we've added a column for FEI. And with that column, you need to add a note here too that fans shall meet or exceed the scheduled FEI value and be licensed to be able to AMCA CRP seal for FEI. That will make sure that you're getting the best fan selection for your application, regardless of the code, regardless of the code requirements. Codes are, as they've been referred to me, codes are like they're the minimum. They're an ankle breaker. Some people refer to them as. And the analogy I always give is, how many of us, if you have kids, how many of you send your kids to school and say, hey, just teach them the minimum. We don't really care if they excel at what they do. Just teach them the minimum. That's good enough. You talk about indoor air quality. When COVID was a big deal, everybody's talking about indoor air quality. We were talking, did we talk about, hey, just make the air just good enough for me to breathe? That's fine. I don't need any better than that. The same thing applies here. You don't need to select the minimally compliant fan for your application, and you shouldn't. You should select the fan that's best for your application, that's going to give you the best overall performance and minimum energy consumption. So, and the way you do that is by scheduling FEI and adding a note and spec related to that.